Good morning, everyone, and welcome to this webinar. This is the 39th ETP4HPC webinar. Can you believe it? I'm Pascal. I'm ETP4HPC's Communication Manager. And for those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in HPC. And we are a private member of the EuroHPC-JU, and our role is to propose research priorities for Europe. And that's exactly what we are going to talk about today, because the two topics that we are going to address today are taken from our strategic research agenda. Now, before I hand over to our speakers, I would like to share a couple of practical information with you. So this webinar is recorded, and you will receive the link to the recording. This webinar is in listen-only mode, but you can use the GoToWebinar control panel to ask questions. We will take all of your questions at the end of the webinar. You can see the chat. We share some information in the chat, and we will share the questions in the chat. And you can see the list of attendees, and you can download handouts. Now, today in the handout section, you can find the two white papers we are going to talk about. You can download them directly from this webinar, and you can find as well the slides. Today's slides are in the handout section, so go there and download them if you're interested. Now, our speakers today, I'm very happy to welcome Dr. Dirk Pleiter. He's a professor of computer architectures at the University of Groningen, and you perhaps know him also better in his former role at KTH. And Dr. Valeria Bartsch is a senior scientist at Fraunhofer, and she recently moved to the Fraunhofer Center for Maritime Logistics. And Dr. Sai Narasimhamurthy, he's our SRA leader at ETP4HPC. He's the one who coordinated all this SRA effort, and he will give a word of introduction over the agenda. This is today's agenda. Now, Sai, did you want to share a few words with our audience?
Yeah, of course. I mean, most of you might have been aware of the SRA, but just to give you a very quick summary, so it's ETP4HPC's strategic roadmap for R&I for the next sort of 5-year time frame. So the main document talks about the key R&I recommendations that we have. So I would encourage you all to go and have a look at our main SRA document. And we have sort of around 13 sub areas that corresponds to white papers. And we have already discussed some of those topics already, such as architectures and non-conventional architectures and system software and things like that. So today we are going to deep dive into two very interesting topics, maths and algorithms and quantum for HPC. Many of you might have been, of course, seeing a lot about quantum these days. So it'll be good to get Valeria's perspectives, and also maths and algorithms. There's a lot going on, especially with AI sort of like disrupting things a bit. What's happening on the maths and algorithms side of things. So there's some interesting perspectives that we'll hear today from our leads for each of these work groups. So yeah, hopefully everyone's waiting to hear from them.
So, Dirk, I have invited you to share your slides, so you can go ahead.
Yeah, thank you very much. I'm aware that there's some delays. I hope you can see the slides now.
Yes.
Okay. Yeah. So it's a great pleasure of being, say again, also part of the ETP4HPC webinars. And it was also a great pleasure of being part of this SRA 6 effort, where mathematical methods and algorithms joined as a topic a little bit later, but we are now, say, there for the third time, again, also with a very engaged team, which I will also say present at the end of this presentation today. Now, when talking about mathematical methods and algorithms, I think it's important to be aware that it plays really multiple roles when we think about it in the context of HPC. Now, probably many of you will primarily think about it of using mathematical methods and algorithms for ensuring more efficient use of the current and also future HPC architectures. But as already was highlighted by Sai, I mean, when talking about AI, we are also talking about new ways of using HPC systems, and for instance, also digital twins belong in this category, and also there, mathematical methods and algorithms play a very important role. But there is a kind of an also backward looking other direction for mathematical methods and algorithms, namely for using these methods and algorithms for actually creating new HPC solutions which are novel and also say competitive on the market. And also this is something which we try to address in this working group and then in the white paper for SRA 6. And then the final topic, which we also address in this context, I will not talk about it today because we have Valeria here. It's about facilitating the use of future non-von Neumann computer architectures that includes, in particular, quantum computing, but not only quantum computing. I would particularly also like, for instance, highlight other avenues, like, for instance, neuromorphic computing. Now, in this presentation, I will take you through the white paper, and of course, there are a lot of details in there. I would definitely recommend of looking into it. But I give you here, say, an overview about, say, how we organized this white paper, and that's where I take you through. So we looked, of course, into the question of scalable algorithms, but we also looked into, say, more recent topics like how to do approximate computing, what's about correctness, also the relation between resilience and correctness. Then a chapter which we also had in previous SRAs was about numerical combinatorial mathematical libraries, which is more oriented to how can we actually say productize more fundamental research on mathematical methods and algorithms. And then the already highlighted chapter on mathematical methods and algorithms for HPC technologies. I will skip the quantum and hybrid algorithms, and then of course I will finish with a summary and some conclusions. So let's first start with the scalable algorithms. So our approach in general was for each of the topics which we say addressed within this part of the SRA to come up with, say, a clear rationale on why do we think it's say relevant in the context of high performance computing. Look at what is the state of the art, and then, and that is of course the main purpose of this strategic research agenda, identify what are future challenges there. Now, when it comes to scalability, obviously the question of communication avoidance and the hiding of communication is, say, an ongoing topic, which is driven by, say, the still growing discrepancy between data processing and data transport capabilities. We all know that data processing capabilities are growing at a faster pace than data transport capabilities. And this has already been a topic since a long time in the development of algorithms. There had also been in the last couple of years still a lot of ongoing work on, in particular, asynchronous iterative solvers. But what we observe, and that's where we see also, say, the future challenge, that the work in particular has a lot of focus in the context of iterative solvers. And the question is, where can we, say, apply what we have learned about communication hiding and avoidance beyond iterative solvers? Now, the second obvious topic is how to also deal with the increased amount of parallelism which we have in our systems. And in particular, as we see for more and more application, that the hardware level parallelism exceeds application level parallelism, which means that we have to rethink also applications in the way of how they can expose more parallelism, which you then can exploit on the hardware level. Now, one of the avenues which have been, say, explored already since a couple of years is parallel in time algorithms, where you then have a parallelization in time, giving you, say, yet another dimension for, say, parallelization. What we here observe that despite, say, quite significant effort and also quite a number of success stories, they have not been, say, particularly well integrated into applications. So that's where, say, we see a future challenge, as well as also, say, efforts to really push the limits of parallel efficiencies when it comes also to new systems. Now, a final topic in this context, which my impression is often a bit underestimated, is that okay, we all agree that our computer architectures for high performance computing and beyond become more and more parallel. But what is maybe not that much in the focus is that we also have increasingly more levels of parallelism. I mean, obviously, all of us have learned that, from single core CPUs, we move to multi-core CPUs, but also within this CPU core, we have, also increasing amount of parallelism, which is often not that well exploited. I mean, let's think about SIMD instructions, but also now with the strong push towards RISC-V with RISC-V argv, so this vector length agnostic vector instruction set extension of RISC-V, we will get here quite some significant parallelism. But then, of course, we have the node level parallelism, not only in terms of having, say, 2 sockets of CPUs, but also having more GPUs, which, say, expose parallelism, and then, of course, the system level parallelism. The question is now, can we, formulate the algorithm such that we have, say, more flexibility to exploit the different levels of parallelism? Because if you compare the different devices, they have a different mix of parallelism. Some have, say, more SIMD pipelines, the other have wider SIMD pipelines, but less of these pipelines, and so on. And it's also a question about, say, custom features. What is meant there is that we also see new instructions emerging, like, for instance, instructions which support matrix and tensor operations. ARM's SME is a recent example for that, where again we have to see, okay, how can we efficiently exploit them at the algorithmic level, in particular for algorithms which are not, say, focusing on dense matrix-matrix multiplication in the case of these SME instructions. And another topic which comes up in this context is, if we have this increased parallelism at multiple levels, how about, say, load balancing? Also, there a lot of fundamental research has been performed in the last couple of years, but there is still much more which needs to be done, as well as also pushing that to a more, say, productive level so that people can integrate it in their application. Now, moving to a next chapter, which was about approximate computing and correctness. And here I want to highlight, say, this topic of low precision arithmetics. I mean, we all know that in particular in the context of, say, machine learning algorithms, which can deal with, say, lower precision arithmetics, we see hardware vendors, in particular when it comes to GPUs, in ramping up their support of low precision arithmetics, and maybe even, say, reduce their support of high precision arithmetics. And that goes now even all the way down to FP8. So you have just 8 bits to represent your floating points. Now, this has already driven, say, a lot of further efforts connecting to, say, decades of research on mixed precision algorithms, but we see a lot of progress there. But still, there is a number of upcoming challenges which still have not been addressed. And this also starts with very fundamental questions about, can we establish, if we, say, make such strong compromises attempt the precision of floating point arithmetics, can we actually define rigorous error bounds? And what recent research has also shown is that established methods for defining these kind of error bounds are not necessarily working that well if we push, say, the number of bits used for these floating point arithmetics to the extreme. And another topic too, which we identified in this context, is also the question of exploring new rounding methods. I mean, there is work which, for instance, has shown that using, for instance, stochastic rounding is actually a quite successful approach in this context. Okay, coming to the next section on resilience and correctness. And here I want to highlight 2 subtopics. First, the question of checkpointing, which has been, say, is often seen as one of, say, the promising way of how to address, say, resilience in our, say, more and more complex HPC architectures. But frequent checkpointing is impractical and also quite expensive. So also here, there is the question whether we can, say, with further efforts in mathematical methods and algorithms help here. For instance, there had also been in the recent years, again, a new interest in working on algorithmic-based fault tolerance, so algorithms which can deal with faults. But there also people started to explore new strategies, for instance, to use machine learning methods for fault prediction and then implement adaptive fault tolerance, which again would allow to reduce, for instance, the number of checkpoints which are done. Now, still there remain challenges. How can we, say, for instance, have fault-tolerant algorithms which also work in heterogeneous architectures when, for instance, GPUs are involved? And still also, even so, fault-tolerant algorithms are quite promising. the number of algorithms which are currently considered is still pretty small, and the question is, can we say support a broader range of algorithms? Another topic which becomes more and more relevant, since we are starting to use more and more also AI for actually generating code, is how can we ensure the software correctness? And there had already been a longer tradition in the HPC community for MPI verification tools, but I think we also need to look more in what is done in the broader computer science community in terms, for instance, also using formal rules-based machine checkable methods for correctness assurance, or efforts to formalize code so that the serial improver environments can be used to actually also, for instance, generate code together also with proofs. Now, a challenge which we see in particular in the context of high performance computing is how can we actually expand the scope of this kind of, say, applied research? I mean, I already mentioned, say, the efforts of using it for checking the correctness of MPI programs, but what about, for instance, network drivers and fabric abstractions? How about, say, compilers and libraries? And also, say, more general tools for analyzing the correctness of parallel codes. Switching gears to the next section, and that's where we again think about more new ways of how HPC systems are being used. So we see a push towards not only using what in many areas are called mechanistic models, which say is more, say, also the history of high performance computing, so that we have simulation models, for instance, based also on physics theories, and to combine them now actually with data-driven models so that we arrive at hybrid models. This has now been shown for an increasing number of cases that this is quite successful, because it makes it also possible to model things where mechanistic models would be much too slow. It would limit ourselves to much too small systems. And that's where we can, say, take benefit of the data-driven modeling approach. Now, what we observe is that there have been, say, many piloting efforts, but in this group we were actually arguing that there needs to be a more mainstream support for implementing these hybrid modeling workflows. And to address, for instance, also questions about how can we actually guarantee the accuracy of these hybrid models. In many areas, also areas where I'm coming from, I mean, we have done over decades a lot of work on how to understand the errors of our mechanistic models. But how does it look like if we combine these mechanistic models with data-driven models? And also, say, the questions of data assimilation becomes then to play a role, because that's how the data-driven models are then developed. Another topic here is when we look into, say, the neural networks, even so, they have been quite successful, but we should not forget, this is despite that we have quite a lack of understanding of their properties and the training methods. And also here we would argue that we need to increase our understanding of the effect of neural network architectures and the training methods. And there are, say, multiple avenues to address this. For instance, maybe we should use this very wide area of research on complex systems, of taking this as an approach of interpreting, say, what is going on in neural networks, which are often treated as black boxes. Can also, say, a move towards multi-level neural networks, which is also a way of reducing the complexity, help us in this case. And then also coming back to already mentioned topic of uncertainty quantification in neural network predictions. And that's where I was admittedly myself quite surprised of how little work has actually been done, for instance, with uncertainty quantification when it comes to these hybrid modeling approaches. Now, the next section is about numerical and combinatorial and mathematical libraries. Now, the general rationale for this is that we have a lot, and as was also, say, highlighted by Sai, a quite vibrant community of, say, researchers and mathematicians and numerical scientists developing algorithms, but there is still a very wide bridge to build often on moving these algorithms into well-tested HPC software, and this software being integrated in real applications. And this, for instance, applies to various areas, and one of these areas is, for instance, multi-scale and multi-physics simulation methods. There are many examples of complex physical systems which require such modeling approaches, for instance, in biomedicine, fusion physics, but also more further applied areas like wind farm energy and so on. Now, the challenge which we see here is really, I mean, how can we further develop mathematical numerical software libraries for these kind of multi-scale and multi-physics simulations, including also the work on coupling libraries, such that they actually preserve parallel efficiency, because you couple here different applications which have different properties also with respect to their parallel efficiency. Another topic in this context we would like to highlight is also this question of model calibration and uncertainty quantifications. The challenge here is that when we look at the calibration of data-driven models using, say, measurement data, this can become quite challenging, in particular when we are talking about very large data sets and ending up with very expensive inverse problems. So also here we need to push existing algorithms and methods so that they reach, say, really a productive usage level, and in particular also taking into account, say, the gaps which we have when it comes to accuracy and modeling of the accuracy and quantifying, say, uncertainties. Now, a final area which I want to highlight is the question of how can we actually use mathematical methods and algorithms in the context of pushing HPC as a technology and market itself. And there's two areas which I want to highlight. It's the area of scheduling and resource allocation, which is, say, inherently, from a mathematical perspective, a very challenging issue, because many of the scheduling problems, they are NP hard. And we have, say, some heuristic methods in HPC which work pretty well, but how about how well do they actually work when, say, our HPC systems become increasingly heterogeneous? How about HPC systems becoming part of a compute continuum infrastructure, and we not only want to schedule tasks on the HPC system, but we also want to schedule the tasks which are running on other parts of this compute continuum infrastructure. That could, for instance, be some containers running in a cloud instance, but also on edge devices. So that's where we are quickly into these well-known challenges like co-scheduling of complex workflows, which extend a single HPC system, co-allocation of resources within heterogeneous HPC system, so where we have, say, different types of compute, but also, say, storage. Also here, support of malleability can be a way of making things easier. At this point, we typically have, say, mainly a single objective scheduling, but what we would need is a multi-objective scheduling. There are many methods known, but how to make them really amenable for HPC users, keeping in mind that they are addressing NP complex problems, is an ongoing challenge. And finally, there is this topic of scheduling and resource allocation in the context of federated and compute continuum infrastructures, which is in particular relevant now. Also, EuroHPC is moving to a setup where the different EuroHPC sites are integrated into a single federation. Now, another topic which I want to highlight here is altitude-tuning. And the reason for highlighting it is that we observe, on the one hand, that in particular in the area of machine learning, we have a number of libraries which heavily rely on altitude-tuning as well as just-in-time code generation. But all this is done on a very hardware-specific manner. So if we want to bring this together with, say, the ambition and having more and more hardware architectures actually developed in Europe, we definitely also have to invest into how can we get all this altitude-tuning support in numerical libraries also available, making it supporting these new hardware architectures. And also here, we don't have to forget that it's a very challenging, even if you have, say, developed, say, the basic methodologies, how to facilitate the vertical integration into the HPC software stacks. With that, let me summarize and conclude. So I have shown you, taking you through quite a different research and development efforts related to mathematical methods and algorithms, and tried also to highlight that they play different roles in HPC, coming from, say, looking, for instance, efficient use of HPC systems, where it's about the scalability, but also, say, approximate computing. We talked about new ways of using HPC systems, in particular when we think about the topic of hybrid modeling, but it's also about a novel HPC solution. That was the final topic. How about schedulers or altitude-tuning software libraries for hardware which is say, being developed in Europe. Not covered here, but it will be a topic then of the next talk, how we also say have algorithms and mathematical methods to facilitate the use of future non-von Neumann computer architectures, because we definitely need these if we want to have real breakthroughs, for instance, in terms of energy efficiency. With that, I hope that I could convince you that new and improved mathematical methods and algorithms are really needed for the upcoming challenges that require HPC resources. And I think the really good and positive experience again in this SRA was that ETP4HPC is able to connect a very active community of researchers in different organizations, also industry organizations. And that brings me to my final slide, where I want to acknowledge the really very engaged contributions of all the different members of this working group. And I can really definitely encourage, once there will be, say, a call from ETP4HPC for an SRA 7, think about it of joining these working groups. It is, of course, extra effort, but I would say this really pays off. With that, thank you very much.
Thank you very much, Dirk. Thank you very much. So I will hand over to Valeria. Valeria, you should receive a message to open your presentation. And to our audience, if you have questions to our speakers, do remember that you can use the questions tool at any time, but we will address your questions at the end. Thank you, Valeria. The floor is yours.
Okay, thank you very much, and thank you also, Dirk, for making the scene ready for this Quantum for HPC talk.
Yeah, he was very good at it, wasn't he?
Yes. So I'm also here presenting for a lot of different people throughout Europe, and I put my thanks to the authors in the beginning. So my co-author was Christa Michelsen from Forschungszentrum Jülich, and then we have a lot of different people from all over Europe who have contributed to our white paper, which is on quantum for HPC. I probably have to make sure that you have the right kind of expectations, because as I have to say, it's not too much about quantum. It is more about how to integrate quantum and HPC into each other. So I'm not going into the algorithms themselves and speaking about how they are working. But of course, if you have questions about it, I'm able to answer. So we also had already, So we also already had another white paper a few years ago, and I was basing this presentation on the previous one, and I was delighted to see that things are changing, which means things are progressing, and that's good. Basically, our motivation is that quantum computing is a future accelerator for HPC systems. We don't foresee in the mid-term future that actually there will be more to quantum computing than to accelerate especially algorithms which are difficult to run on HPC systems. However, at the moment, when we are still in the noisy intermediate quantum era, what we see is that all of our algorithms are hybrid, so they are iterating between quantum and classical computing resources. And that already means that already on this level, one sees the need that there is that we need to integrate HPC and quantum computing on different levels. And these are the system level, the programming level, and the application level. And here I'm concentrating more on the integration on these different levels in the remaining talk. So I want to give the highlights of our recommendations and priorities that we suggested in the beginning. And these are that we want to make sure that applications are considered in the hardware-software co-design. This is very important because the applications are going to change. it is quite clear that we are reaching on a hardware level. We are already the point where logical qubits can be formed. And that means we are going into an era of early fault-tolerant quantum computing algorithms. And so we have to consider and keep in mind that we don't yet have the killer applications. We don't yet have the application of an industrial relevant problem which can really speed up compared to classical compute. And we know that things are going to change, so we have to keep that in mind and make sure that we always have these applications and have a ongoing hardware-software co-design. What we also believe is important, that we facilitate an open source software stack that supports the European hardware, and that's especially important because there are right now a lot of startups in Europe with different ideas how one can build quantum computing hardware. And as we have seen in other areas of HPC, it is important to have the software stack that makes it easy for users to use it. Otherwise, you will be in trouble. So an open source software stack is important for the quantum computing industry in Europe. Then again, going to application, at the moment it is, and hardware together, at the moment it is very difficult to see which hardware fits to which application domain or kind of, or which method fits best on which hardware. And here we believe it's important to benchmark in an application-oriented way. So there are different, as I will explain later, one can, of course, benchmarking can be applied to different parts of the quantum computing hardware. But if we do it in an application-oriented way, it would facilitate the way towards really comparing different platforms for different algorithms, and to also, of course, compare cross-platform with classical compute to see where we are with quantum. What we also would recommend is to approach the middleware design in a holistic way. And another thing where Europe is quite strong, it is the emulation of quantum computing on classical hardware. So this is already something where we are good at, but in the future we still need to be good at it, because we also believe that this emulation has come to stay. It's not something we are doing right now because the hardware isn't good enough, but I believe that it's going to stay for a while. So concerning applications and algorithms, I'm not talking very much about the applications in this presentation as explained earlier. However, there is progress in Europe because the Quantum Center of Excellence are starting soon, and they provide a lot of different use cases from various domains. So this is something we had in the last SRA and said, okay, this is important to do, so we can do, okay, check, this effort has started. However, if we still can give a recommendation, it's probably the recommendation that right now a lot of effort is put into these hybrid algorithms. However, the hybrid quantum classical algorithms are also a part of a longer running workflow, and this also has to be taken into account. So, so you don't, I mean, like, of course, it is good to have to accelerate an algorithm, but after you've done it, you still have a much larger application which still needs to be accelerated, and that has to be kept in mind. Concerning the benchmarking, there are, I mean, like, it's first of all important to define exactly what you want to do with benchmarking, because you can do a lot and call it benchmarking. And there's certainly a level which we call vertical, which goes from the hardware level up to these application-centric benchmarking, and then you have this horizontal level where you are, for example, comparing different quantum computing systems, or even have a cross-platform benchmarking, for example, with classical HPC systems. And concerning benchmarking, what people are focusing on is often the time to solution. However, one can also have different optimization objectives, such as the energy efficiency, which for many different hardware solutions in quantum looks better compared to classical HPC. So here we believe that a hardware-software co-design is essential, and a broad set of applications is needed for this benchmarking. Plus, it is really important to develop a widely acknowledged ranking system. Right now, I think what most people can agree on is this quantum volume benchmark. However, that's kind of only half of the story, and to put it more, to see more like how can quantum computing give benefits to applications looks to us like the way forward. Concerning the hardware-software stack, we have kind of made this distinction here between application and user-related software and system-related software. So the application and user-related software is basically everything that the user sees. However, it might also encompass different parts of the software stack, because we have quite heterogeneous end users, which are different in needs of in terms of software tools. For example, we have really users that are going close to the hardware and might go deeper into the stack here. The middleware typically is closely associated with the nature of the quantum computing processing units. There are very different hardwares out there, and here the middleware needs to make sure that that it is as transparent to the users as it can. Of course, it might be difficult seeing that you have, for example, this gate-based approach, which is sometimes also called universal or digital, and then you have analog systems like quantum annealers or Rydberg simulators, or completely different systems which each have different programming paradigms. So that's a very tough thing here for middleware to provide, but it is important so that users can use different hardware in the end. Concerning the application and user-related software, basically all of this software exists at some level. However, the goal is to have a higher maturity level. So there's a research effort needed for interfaces, libraries, high-level programming models and languages, as well as compilers. Concerning the system-related software, this is something that can be attacked very easily from an HPC perspective, because basically one can think of quantum computing as a limited and expensive compute resource. And if one does that, then from the HPC tools, there are tools which are already there. So, for example, scheduling mechanisms that optimize the usage of the resource. You probably also need multi-level schedulers, because you have different timings. When you call the quantum computer, you have the time between the shots, which is usually very quick. Then, because you often have these quantum hybrid algorithms which run iteratively, you have the time between the iterations. And then if you think about this longer workflow of a whole application, you're offloading tasks where some of them are supported by quantum computing and some of them are not. So this is again a different timing here which is needed. And here a standardized approach is required. And because quantum computing is a limited and expensive compute resource, a billing is necessary. So you need to have a good accounting mechanism, authentication mechanism, and monitoring mechanism applied. So concerning the system integration, we are seeing at the moment the deployment of quantum computing systems at HPC centers in Europe. So this is clearly something which goes beyond what we could present last time around. And we can see that quantum computing is co-located at HPC systems, so we are seeing a progress beyond the pure cloud system approach, which has been prevalent before that. So one can see, or the expert report already several challenges, but it's likely that there are new challenges upcoming once this really hits reality and the integration starts really in a serious way. And these challenges are on the infrastructure level, the interconnection networks, and which have to be defined on hardware and protocol level. So you have a hardware, so you need to define a hardware agnostic layer to allow users to benchmark on different systems. And you have different levels of maturity between the HPC and quantum computing software stack. You need hybrid quantum computing scheduling policies, and probably a lot more things which we haven't thought about yet, but which will come in the near future. A last point I want to make, it's really the last slide of this presentation, is the emulators for quantum computing. So emulating quantum computers with HPC devices. I have put here a life cycle about emulation. What you usually do is that you think about an algorithm, you put that into a noiseless emulation, verify if your algorithm can work, then move into the noisy emulation and prepare the deployment on real machine, do hardware runs, and probably see that things probably didn't work as you hoped, and you might start your life cycle again with noiseless or with the noisy emulation and change your algorithm accordingly. So our belief is that although there are limits about how big the systems are that you can actually emulate, at the moment the limit is at 45 qubits, emulation is going to stay because of its usefulness for the design, the analysis, and the benchmarking of quantum computing algorithms. And because you can study new qubit technologies or new parameters for your existing technology and see how that can influence your algorithm. The good thing about emulation is that it allows a step-by-step analysis of quantum computing algorithms, and therefore you are able to change your algorithms much easier when you're running them on emulators and see where the deficits of these algorithms are. So here I'm coming to the end of my presentation, and I guess that Pascal is going to go on with the questions. Okay.
Okay, yeah. So it's question time. Sorry, just give me a minute to share my screen. Where am I? Yep, here. Okay, so we already have two questions from the audience. They are both for Dirk. So I have copied the questions into the chat so for everybody to see. So first question is from Sabri Plana. Hi, Sabri. So question for Dirk. Are there any noteworthy developments in AI-enabled multi-objective scheduling in the context of computing continuum?
Yes, thank you, Sabi, for this question. It's a difficult question because there are, say, several developments in this context, and I think there, when we first of all, there is when you think about this problem, I mean, you have to first start to think about, okay, how can I actually formulate here a multi-objective optimization problem? And that already turns out to be a non-trivial, say, challenge. But I think there have been, say, quite some interesting progress which have been made. I'm sure that you're also aware, and this is, by the way, also cited in our white paper, the work at the Vienna Technical University. When it comes to then using then AI, or maybe better say machine learning methods in this context, I see currently, say, two possible avenues. One of them has been explored a bit more than the other one. So one is that you essentially try to use machine learning methods in order to make a prediction about the future state of the system and take this into account, possibly also in an heuristic scheduling decision. There have been a lot of efforts in this direction, also more specific in HPC context, but I personally would say my conclusion is that has not been, say, too successful, and that may in part be due to the two reasons. I mean, it's the difficulty actually, at least for many HPC systems, as they are used for quite different workloads by many different users at the same time, to actually make good predictions. And on the other hand, the question, okay, what are actually predictions which are, say, really relevant for making decisions? I would claim so far, say, again, scheduling in combination with backfilling, at least for HPC, is still, say, one of the most promising avenue. Another direction is when we think about, say, using AI of maybe providing good enough answers to optimization problems. I haven't seen too much work in this direction, but that I think is certainly, say, something which would be worthwhile further exploring, because once you want to make scheduling decisions based on mathematical sound solution of say, an optimization problem, that can be, say, too expensive, even for HPC, where you could say, okay, I mean, I take a few minutes for making a scheduling decision. And that's where possibly, say, machine learning methods could actually help. But I'm at this point not aware of, say, really much new work in this direction. But it's certainly, say, something where I would expect more research to come up, and it's also worthwhile of pursuing that.
Thank you, Dirk. So here is another question for you from Henry Strauss. Dirk, you were talking about mixed precision. Do you know Gustafsson's work on a new number format? And if so, can you please comment on how it fits in your work?
Yeah, thanks, Henry, for this question. Again, it's quite a difficult question. I am say it's not my main area of expertise, in the sense of that I'm not aware of, say, recent work where, say, there wasn't really a comparison of the different floating point formats. If you just look at the market, I would say the number formats which have been proposed by Gustafsson have not been, say, too successful in uptake on the market. That doesn't necessarily mean that from a numeric perspective that they would still be, say, a good idea. What I believe would be necessary is, say, having further exploration on what are also, say, the trade-offs in the specific cases. And I think it's very difficult to actually come up with some predictions. So when you, for instance, look in the area of, say, iterative solvers, I mean, an avenue which has been, say, used since many times is to say, okay, I mean, you combine, you have essentially a kind of a nested solution approach where you have a preconditioner, which, because it's a preconditioner, you don't have to solve very precisely, and then you use then a reduced precision for actually doing the computations, while the real solver then with this flexible preconditioning is used in high precision. Now, obviously, there are some trade-offs to be made. I mean, how good does, say, the preconditioner have to be in order to provide you then with actual help in the real solver? So this needs to be explored in specific cases. I think there definitely has been work done in this direction, but more work needs to happen. And in this context, would definitely be interesting to understand, okay, how far can I actually push these limits? So if I go to my old field of research in lattice QCD, I admittedly, I find it hard to believe that if one would say use a preconditioner based on 8-bit floating point precision, probably you would have already lost too much information for this to become, say, a useful preconditioner. But still, I would argue it's very worthwhile of trying it. Even so, of course, you have some efforts because you have to do really then also address, say, the quantification challenge there, because you have just, say, depending, I mean, there's some difference, but you have essentially 3 bits available for the exponent. That means you have a very narrow, say, range of numbers which you then can represent. So you need to, say, quantize it correctly.
Thank you, Dirk. Now we have a question for Valeria. So question from Silvina Caino-Lores from INRIA. One of the issues I see from the HPC side is access to use cases and hardware resources to experiment with. How can we get in touch with the quantum ecosystem you mentioned?
Yeah, so basically, I am quite aware of what happens in Jülich for some reasons. I mean, like probably just because it's the closest HPC center to where I live, so, which is a good enough reason, I guess, sometimes. And they at the moment have a D-Wave quantum computer, plus they are building up a Pascal system. And here you can apply for compute time in order to run on that. I have talked to my colleague from CEA, and they also do have Pascal system. And I know that that there are also possibilities to run on that. I don't know exactly about the way how you apply for that, but that's probably also application based. I mean, like if you have an application that that the decision is based on that. But I guess that a lot of at the moment a lot of these quantum computers are still being built up. For example, Kilimanjaro is right now being built at the Barcelona quantum. But not supercomputing center, not yet, but we are working on it. And, because I'm trying to answer your question as good as possible, and I'm sorry, and then I'm starting to stammer because I see that there's also a second side of it, which is the access to the use cases. And here, what people are building within these quantum centers of excellence is probably also libraries of use cases, and these projects are yet to start or are just starting. So at the moment, this is not yet happening, that we already have all the use cases somewhere on a web page. But concerning the hardware resources, I would love to follow up on that and give you a more complete list than just what I can think about right now on the spot. So, yeah.
Sai, you wanted to comment on this because you sent a message about it, but it was a private message. So did you want to comment on it?
Sure. Yeah, just following up from Silvina's question. So I'm just thinking that it's great that we have now the infrastructure starting to be in place in Europe. I'm just starting to think of the users, Valeria. I mean, how can we as a technology community help these new users to use the new quantum systems, and do they have good understanding of using these new infrastructures? Because typically there have been HPC community, now they have the quantum resources in place. I mean, is there some element of education and training needed? Just I'm thinking about what are the pain points here, Valeria?
I mean, there is the Euro HPC master program running, and they also do have a winter school, summer school on quantum computing. There are a lot of quantum computing summer and winter schools running. I mean, almost too many. So I guess for students, it's quite easy to get in touch and get things running. And concerning, I mean, like people who are already working, I mean, of course, they can go to one of those many summer and winter schools, but yeah, I guess that there are a lot of resources on the internet. Really, I mean, like you should be a lot of material out there concerning that the European projects. I guess you can reach out to these HPCQS project, which is
HPCQS.
already, it's already running
Yeah.
since quite a while. So,
Yeah.
so people, there's an established thing, right, ongoing, and it's not like we are starting. So that might be a good point of contact in the European way. And yeah, I don't know, like there's so much out there that it's difficult to pinpoint, really. I mean, like that depends what you need, I guess. Kind of.
No, I think this is a great point. There are some projects like HPCQS which have been ongoing. I think there's a lot of lessons learned from there. I think learning their experiences and liaising with them. I think, and maybe other quantum projects as well, right? Some of them. So QSolid and maybe some of the other ones. Maybe it might be good to learn from some of them.
Yes,
And,
yes. I mean, there
some
are more projects.
national
Yeah.
initiatives as well in different countries.
Yeah.
Okay.
Yeah, there
Thank you,
are a lot more projects out there, and you can look at it. There is this quantum flagship in Europe, and
Quantum
there are
flagship.
projects out there. And maybe for your application area, you find the right kind of project and can then pinpoint those people.
Yeah, good
Yeah,
thoughts,
I
Valeria.
don't know.
Thank
I
you.
don't know if it may be of interest, but I saw a workshop, an EU Master for HPC workshop advertised. It's going to take place in June, and it's called HPC and Quantum Computing.
Yeah, that
So
might be interesting. Yeah.
that might be interesting. It's open. It's not open to everyone, but it's open to affiliated to individuals affiliated to a partner organization, and ETP4HPC is a partner organization of this workshop. So if you go to our to the ETP4HPC LinkedIn, I have reposted this announcement by EU Master for HPC, so it might be of interest to you. Just a small thing, but it's happening soon. So
Yeah, thank you, Pascal. Yeah, hopefully people can make a note of that as well. I think we as a community need to learn a lot about quantum systems and their usage.
Okay, any other question? No, I don't see any other question coming in. We still have time for one more question, so just in case, it's still time to enter your question. Otherwise, Sai, Valeria, Dirk, well, thank you, first of all. Thank you to Valeria and Dirk. And did you
Thank
want
you.
to add anything to this, or Sai? No?
So maybe I can just ask very quickly. So Valeria and Dirk, are there any new, what's your new interesting areas you're working on? So maybe you want to just say a couple of words on that. I know you've done a lot of work in these areas. So what are you doing these days, Valeria?
I mean, like what I'm what I'm doing. Okay, what I'm interested in is really like optimization algorithms. I think that's very interesting, especially because I've been working on quantum chemistry beforehand, and there it was clear it has to be gate-based, and optimization completely different game. Annealer is much more important, and that's really interesting. Plus, also what I was underestimating a few years ago were these quantum-inspired algorithms. It was always like, no, go for quantum computing, don't go for quantum-inspired. But now with the tensor networks, there are now methods around which can really accelerate stuff. I mean, like especially PDEs can be really accelerated with these tensor network methods, and that's something amazing, and that's also something that I would love to work on in future. Yeah.
Thank you. Thanks, Dirk.
Yeah, and as far as my research is concerned, I'm shifting a bit more to also say future technologies, and then I get actually quite close to also say some of the research interests of Valeria in trying to understand of how we can say connect say mathematical masses and algorithms which we have which we know from the past onto completely new say computing architectures, where Valeria's focus is on quantum computing. My focus will be on neuromorphic computing, which is another area of also unconventional hardware architectures, in particular when in combination with in-memory computing, where I see, say, a lot of opportunities also then to really significantly reduce the energy consumption, which we are facing with, say, the more conventional architectures, where I keep people reminding it's based on principles which have been, say, developed in the 1940s and shortly thereafter. They have been amazingly successful, but we also see the limits by now, and it's say extremely exciting to look into what can we actually do beyond, because a lot of it has been ignored because, say, what we have been doing on, say, the conventional architectures based on, say, binary representation of information, the von Neumann architecture, the CMOS technology has been so amazingly successful.
Great. Thank you. Yeah, very interesting. Yeah, Pascal, back to you then.
Thank you, everyone. Yeah, I just put the URL of the workshop I was mentioning earlier, just in case it can be of any use to our audience. So it's in the chat. So, well, it's time. We are right on time. Wonderful. I love it when it works smoothly. So, thank you, everyone. Thank you to our audience. I hope to talk to you again on the 20th of June, because that's our next webinar, and we will tackle again 2 topics from the SRA, and it will be AI and foundational models and hardware components. So, very interesting topics once again. So thanks again to Valeria and Dirk. Thanks to Sai, and talk to you soon.
Yeah,
Bye
thank you,
bye.
Pascal. Thanks, everyone. Bye.
Thank you. Bye-bye.